So in this lecture, we're going to continue our discussion of counting. We're going to talk about the two situations in which order matters. So for this lecture, we're going to assume order matters. Okay, so we have a repeated experiment. Experiment is repeated r times. We have n distinguishable outcomes, at least initially. Okay. Here we're going to look at the situation in which order matters, and we're going to do with and without replacement. So here, just a simple example, we're going to do flipping a coin 3 times. Right? I want to know how many outcomes could there be. Right? So maybe it's pretty obvious that there are 8 possible outcomes. So 2 outcomes for the first flip, 2 outcomes for the second, 2 for the third. This is an example of the counting with trees that we mentioned in a previous lecture. Okay? And this is exactly what we're going to do right here. We're going to count with trees. So here we have our set of all possible outcomes, and there are 8 of those. Right? But let's pretend like we don't already know that there are 8 of those. I'm going to split those outcomes up into 2 sets. Those where I get a head on the first flip, and those where I get a tail. So here, this branching can be either heads or tails, and which branch I follow depends on what happens on the first flip. So let's say I haven't done anything, and then I flip the coin once, and then I get either heads or tails, and now I know which branch to follow. Okay. Here there are 2 branches. Next, I'm going to do the second flip, and here I have all of the outcomes with the heads in the first flip, and I'm going to split those up into 2 further subsets. Those where I get a heads on the second flip, and those where I get a tails on the second flip. Over here I have the outcomes where I get a tails on the first flip, and I'm going to split them up according to what happened on the second flip. And then I'm going to go to each of these 4 sets of outcomes and split those up based on what happened on the third flip. And once I do that, I end up with a row of single outcomes. So heads, heads, heads is a single outcome. Heads, heads, tails, etc. So presumably what we would do is start with the single outcomes and then work our way back to figure out what should go in this box. Right? So because initially we don't already have all of the outcomes enumerated, right? But I know that I have 2 outcomes, 2 possible outcomes for the first flip, and then 2 for the second, and then 2 for the third. Okay? So I'm going to have single outcomes, and then I know if I count, well, this box is going to have 2 things in it, okay? Because the 2 possible outcomes here kind of get folded into one box here, and the same thing for these other 3 boxes. So every box in this level is going to have 2 things in it, and then everything in this level is going to have twice as many things as the boxes below it, because everything has 2 branches. So 2 boxes with 2 things is going to become one box with 4 things, and again, 2 boxes with 4 things is going to become one box with 8 things. So the bottom level, I have 1 outcome in each box, and then 2 outcomes in each box, and then 4 in each box, and then up here 8 in the box that contains all of them. So now I can count, it's 8 things. Okay? So this same kind of strategy will work for with replacement and order matters. Start with a big box, and then if there are, here we had 2 possible outcomes, so n was equal to 2, but in general I could have just say n branches here, and then I could have n boxes on the second level. Each one has n branches, and I go down to the bottom. Now the number of levels here is going to be r plus 1, so here I've done 0 experiments so far, and then here I've done 1 experiment, and 2, and then finally after I've done 3. Okay. So if I'm going to do r experiments, I'm going to have r plus 1 levels. Everything in the bottom level will be a single outcome, and I can kind of count backward and figure out that it's going to be every box is going to have n times as many outcomes in it as the boxes below it, because I have one box is going to have n branches with the same number of outcomes. When I fold them all together, it's going to be cardinality will be multiplied by the number of branches, which is n. So here's the same thing without the entries. Right? So here I have the outcomes written in there, heads, heads, tails, etc. Here I can do the same counting argument without actually saying what the entries are. Okay. So here's the general picture. So what we said before, I start out with some box that contains all the outcomes, and I don't already have those enumerated. I don't already know what all the outcomes are, but then I'm going to split these up depending on what happened on the first experiment. Okay, so here in this box I've done 0 experiments. I don't have any outcomes so far, and then I do the first experiment and I get the first result, and there are n possibilities for that. And I split things up based on what happened on the first experiment, and then I split those boxes up further by what happened on the second experiment, and then I split those boxes up further by what happened on the third experiment, and I keep going until after I've done R experiments, everything is split up completely. Each of these boxes on the bottom level will have a single outcome. Okay? So now, presumably, I don't know how many things are in any of these boxes, except on the bottom row. I know each box has one outcome in it. Okay? So now I kind of want to filter that information back up so I can count how many things are in this box up at the top, which is what I really wanted to count the whole time. How many distinguishable outcomes do I have? So these boxes have one thing in them, and this box above them is going to have, well, n things in them, because this box will contain the contents of n boxes below it, and each box below it has one thing in it. So this is going to have n things, and then on the next level I'm going to have the boxes have n things in them, and a box 2 levels up will have n boxes below it. Each one contains n things, so the next one's going to have n squared things. And I keep going up to the top, and then I have n to the r things. Okay, so at the bottom I have one thing, and then n and n squared, and into the third, etc. But the very top will have n to the power r. Okay? So another way to think about that, not in terms of trees, is it's exactly the same computation, but there's no visual component to it. For the first experiment, I have n choices, and that's the n branches here. The second experiment, I have n choices. The third experiment, I have n choices. And the last experiment, I have n choices. Every place, every experiment gives me n possibilities. I multiply all of those, and it's n to the r. So let's move on to an example where order matters, and we're doing without replacement. So here we have Alice and Bob and Charles, and I'm going to choose a president and a vice president, and one person doesn't get any title. Okay, so turns out that there are 6 outcomes here. I'm going to put all 6 of those here, and then I'm going to have a first experiment. The first experiment will be choosing a president. So here, R is going to be 2. One experiment will be choosing a president. The second experiment will be choosing a vice president. And there's 2 experiments, and that's R. N will be equal to 3, because initially I have 3 possible outcomes for choosing the president. 3 people. So I'm going to kind of reach into this group of 3 and pull out one person. That'll be my president. Okay. So I'm going to distinguish the outcomes here by, is the president chosen to be Alice, which is this branch? Is the president chosen to be Bob, which is this branch? Is the president chosen to be Charles, which is this branch? Okay. Okay, so here I had 3 branches, because initially I have n equals 3 people, 3 possible choices for president. After I choose the president, we're assuming that the same person cannot hold both positions. So after I choose the president, I only have 2 choices left for vice president. Now, which 2 choices depends on which box I'm in. Right? So if I chose Alice for the president, then Bob and Charles are my choices for vice president after that. So Bob, Charles. If I chose Bob to be president, then I have Alice and Charles for my choices for vice president. So which choices I have after the first experiment depends on the choice that I made in the first experiment. Right? So I have Bob and Charles if I chose Alice in the first experiment. But the number of choices I have on the second experiment does not depend on which choice I made on the first. So no matter what, I'm going to have 2 choices for the second experiment. Okay? So one person was taken out of the running. When I chose them to be president, they were taken out of the vice presidential running, but I still have 2 people left. So I have 3 options for the first choice, and then 2 options for the second choice. 2 options because one option was depleted in the first choice. Okay? So you end up with 6. Okay? Here's the same picture without the outcomes written in there, and this picture is all I really need to do the counting. These are single outcomes here, okay, and I can see, well, one outcome and one outcome here is going to be 2 here, and then 2 here, 2 here, 2 here means there's going to be 6 here. Okay. So this is the general setup. Is I'm going to have assume I'm going to choose people to hold R different positions, and I have n people initially. Right? So I'm going to choose one person out of the initial group. There are n people in the initial group, and I can choose Alice or Bob or Charles or Danny or whatever. So I have n choices here, and after that choice, one person has been taken out. They're the president, and then I'm going to choose a vice president, and I have n minus 1 choices here. And then in the branches in this level, I'm going to have n minus 2 choices for whatever is next, and then n minus 3, etc. And if I'm going to make r choices, then down here at the bottom, I'm going to have n minus r plus 1 choices at this stage. And you can just see that n choices here, and then n minus 1, n minus 2, etc. Down here, I have n minus the quantity r minus 1 choices, which is the same as n minus r plus 1. So if I've made a certain number of choices, then my number of options for the next choice is the number of choices I've already made, or the number of choices I initially had minus the number I've already made. Okay, so when I get down here to make choice number r, I have already chosen r minus 1 other people, so I have n minus those r minus 1 already chosen people. So that's the reason I have this many choices, n minus r plus 1 here. Okay. So the total number is going to be n times n minus 1 times n minus 2 times all the way down to this number here. Yeah. So we could have combine any of the n choices from the first experiment with any of the n minus 1 choices in the second experiment with any of the n minus 2 choices in the third experiment, and I get different outcomes. Okay. So let's kind of summarize and write down what we found there. For the width replacement, in the first experiment, I have n choices. Right? In the second experiment, I still have n choices, because width replacement means if I see heads in the first, I can still see heads in the second. My number of choices doesn't decrease after any of the experiments. So I have n possible outcomes in the first experiment, and n possible outcomes in the second experiment, and n possible outcomes in the third experiment, and then n possible outcomes in the last experiment, which should be experiment number r. And then I multiply all these. N choices in the first, so I could times n choices in the second, times n choices in the third, and then I get n to the power r. So again, we're multiplying these because of the trees and branches. So I have n boxes, and then each box gives me n minus 1 boxes. So if I want to count the number of boxes on the second level, it's these n boxes each give me n minus 1 more. So it's n times n minus 1. Okay? So the fact that these boxes are kind of accumulating in this way is the reason that we multiply these results. So we figured it out. If I'm doing width replacement and order matters, then if they're n distinguishable outcomes in r experiments, they're n to the power r possible outcomes. If I'm doing without replacement, well, for the first experiment, there are n choices, and whatever choice I make on the first is then removed from the possible outcomes for the later experiments. So for the second experiment, I have n minus 1 choices. Right? So I choose Alice in the first choice for president. I can't choose Alice again for the second choice. Right? So I keep going, and then I get n minus r plus 1 was the number of choices I had on the last one. Okay. So, let's see. So this has a neat little formula here. Okay. N factorial over n minus r factorial. Okay. And the reason that we have this formula here, this kind of concise formula, is because in this row I'm multiplying n and n minus 1, n minus 2 all the way down to this number. Right? So I'll just write it down here. N times n minus 1 dot 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 n minus r plus 1. That is the number of outcomes here. Okay? N times n minus 1 times n minus 2 all the way down to whatever this is. But now I want a kind of a nicer way to write this. So what I'm going to do is say I'm going to multiply and divide by n minus r minus 1 dot 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 all the way down to 1. Okay, so I'm going to take this number and multiply and divide by the same thing. Okay, so I multiplied and divided by this product here. Since I multiplied and divided by it, I didn't change this number, but now I can collect this numerator. That's just the product of everything from n down to 1, which is n factorial. And then this denominator is the product of everything from n minus r down to 1, which is n minus r factorial. Okay, so that's the reason we have this formula. So these things here we call r permutations, or r permutations of n. And we can denote this number by NPR. So N is telling me kind of the size of the set that I can choose from, and R is telling me how many things are going to occur. Okay, so I'm going to have N things to choose from, and R choices will be made. Okay, so these are called R permutations, and this is how many there are. Okay, so what about NPN? If I'm going to, if I have N choices to make, or N possible outcomes, N options for my first choice, and I'm going to make N choices, then this NPN is just N factorial. Right? So if we look back, N factorial over N minus R factorial, if N equals, if R equals N, then N minus R is 0, 0 factorial is 1, so we just get N factorial. So another way to think about that is I have N choices to make for the first one, N minus 1 for the second experiment, N minus 2 for the third, and then when I get down to make the last choice, only one thing remains. So it's N times N minus 1 times N minus 2, etc. It's N factorial. So this is very important. If I have N things, they're N factorial permutations of those N things. Okay, so in this case, we can think about permutations as being all the different ways to put N things in a particular order. So if I have 1, 2, 3, 4, 5 up to N, there are N factorial ways to reorder those terms. Okay, so one more way to think about what we just talked about. Okay, so we want to take this set of all permutations. So here we know there are N factorial permutations for the whole thing. That's very easy to see here. Okay. Now I want to use this to kind of come at NPR a different way. Okay, so I want to take this set of all permutations and split them into subsets. Okay. So in the subset, I'm going to group all the things that are the same for the first R terms, and then I don't care about what's happening later. Right? So take all the permutations and split them up into subsets. Okay, so for whatever A1, A2 up to AR I want to choose, I'm going to group all of the permutations that start with that same group of R terms in that order. Okay, so I know how many permutations there are. They're N factorial. What I'd like to count is how many boxes do I get when I take the set of all permutations and group them in boxes like this. How many boxes do I get? Because the number of boxes is equal to P NPR. Okay. Because if you look, I can take any R permutation, right? So I have N possible outcomes, and I want to look at all the different ways to order R of them. Okay. Each R permutation can be assigned to one and only one box. The set of boxes, or the set of permutations, which start with exactly those R terms in that order. So I take all the permutations and I split them up based on what the first R terms look like, and I want to know how many boxes there are, because each box corresponds to a single R permutation. So all I need to do is figure out how many things are in each box. Well, if I look at the things that start with these R terms, how many different permutations start with those R terms? Well, it's N minus R factorial many of the permutations that start with these terms, because if I start with these terms, I have N minus R terms remaining, and then these wiggly parts over here are just all the different ways to reorder the N minus R remaining terms. We know that if I have N minus R things, there are N minus R factorial ways to reorder them. So if I take any R permutation like this, and just take the remaining N minus R terms and order them however I want, that's going to give me all of these full permutations in these boxes. So I take all the permutations, I split them up based on what the first R terms are, and then each box is going to contain N minus R factorial things. And now I can look down here. I take N factorial things and split them up into a certain number of boxes. Each box contains N minus R factorial things. Then the number of boxes is the total things divided by the number of things in each box, which is N factorial over N minus R factorial, and that is the number of R permutations of N objects. Okay, so that's another explanation for where this formula came from. Okay. So here's a little visual example. This is in the previous page. This is a little abstract. So we have a little visual example. So I want to do 4 P 2, which means I want to know how many ordered sequences of length 2 can I choose if I have 4 things to choose from. So here I have A, B, C, D. Those are my 4 things. I'm going to pick 2 of them and put them in an order. Okay? So what I'm going to do is say, well, I know there are 24 ways to order all 4. So if I take A, B, C, and D, and I ask, how many reorderings can I get just from A, B, C, D? How many permutations are there of those 4 things? It's 4 factorial, which is 24. Right? So what I'm going to do is say take all 24 of those permutations, then I'm going to group them together based on those that have the same first 2 elements. So I have AB and AB on these 2 permutations, and then the last 2 elements are different. Okay? So I group those 2 things together because they have the same first 2 elements. And then this box corresponds to this 2 permutation. Right? This is a 2 permutation. Okay, so I have A, B, C, D. I'm going to choose 2 things from that and put them in order. That's what AB is. Now I'm grouping all of the 4 permutations that start with AB. And I have these 2 that start with AC, etc. So if you look at the top of each box, there's a label. All of those labels correspond to the 2 permutations, right? So 4p2 is 12. Each box corresponds to a single 2 permutation. That's what these labels are. And now I'm grouping the 24 permutations by their first 2 elements. So the first 2 elements, this AB, I'm going to look at these 2 things, the 4 permutations that have those first 2 elements. And now what I'm going to do is say, well, if the first 2 elements are AB, then the last 2 elements are going to be C and D in some order. And I know that there are just 2 ways to order those 2 things, C, D, and DC. So each box is going to have 2 things in it. And I know that I have 24 things distributed among these boxes. So if I have 24 full permutations in the boxes, and each box has 2 things, there have to be 12 boxes. And that's what that is. That's this NPR. So here we're trying to understand NPR based on NPN, which in my opinion is easier to understand. So we figured out order matters and with replacement. That was the first thing we did, and they're N to the R. N choices for the first experiment, N choices for the second, N for the third, etc. Okay, so order matters and without replacement, that was what we just did. That is NPR, which is the same as N factorial over N minus R factorial. Okay, so we're going to do N choices for the first experiment, N minus 1 for the second, N minus 2 for the third, and N minus R plus 1 for the rth experiment. Okay, and that concludes the order matters portion.